Hey math friends, welcome back to video notes. Here we are for AP Calculus. This is Chapter 7, Section 7.1, and this is a combination of the Day 1 and Day 2 notes. Today we're going to begin by talking about mathematical models for real-life situations and how these are often represented by differential equations. That is, an equation that contains an unknown function and some of its derivatives. And this shouldn't be surprising to you because in real life, when we try to make predictions, we often have to use data on how current values are changing in order to predict future changes. So our first challenge is to be able to model the situation with a differential equation. So I have two examples of this. It says to translate the following relationship into a differential equation. The rate that a quantity z changes with respect to time is jointly proportional to y and the square of z. Hopefully this takes you back a little bit to pre-calculus when we worked on writing relationships of things that had direct variation or inverse variation. This is the same thing, except we're going to write this in a differential equation format. So we start with the part right here at the beginning that says that, sorry, working on my pen here, that says that the rate of change, or the rate that a quantity z changes with respect to time. So there's our differential right there, dz dt, is, there's our equal sign, jointly proportional to. Jointly proportional just means that we're going to have multiple things being multiplied together. So jointly proportional to y and the square of z. Now be careful, the square of z is z squared. The square root of z would be the square root of z. So make sure that you know the difference between square and square root. Now the one thing that we're missing here is our constant of proportionality, which has to always go in the numerator of our expression. And you can use whatever letter you'd like, but the common letter that we always see being used for a constant of proportionality is k. So that's the answer for example 1. Let's take a look at example 2. Again, we're looking to translate this relationship into a differential equation. It says the decrease in r with respect to time, so there's the differential part of our expression, dr dt is, there's our equal sign, proportional to, so we know we need a k, proportional to x, so if it's proportional to, it is with the k in the numerator, and inversely proportional to, so this is going to go in the denominator, inversely proportional to the cube root of t. And there's my cube root of t. And that one's done as well. So these really aren't very difficult as long as you're able to pick apart the verbal expression and translate it into mathematics. So it's common for our text and or real life situations to switch between different types of notations, especially when we're dealing with implicit differentiation with equations that contain multiple variables that cannot be separated. Now we've done this before. Earlier this year, we worked on implicit differentiation to find the derivative of a function. And when we learned implicit differentiation, we learned that we can either use our Leibniz notation, which is that dy dx or dr dt or whatever it might be, or we can also use our y prime notation. Remember, y prime would be the derivative of y with respect to x, or dy dx. That means the same thing. I prefer the Leibniz notation because I think that it clearly defines which variable is the dependent variable and which variable is the independent variable. So I think that that notation is a little bit more useful. So for my example 3, it says find the derivative of the following using that Leibniz notation. And recall that taking the derivative of a function with respect to x is d dx of both sides of the equal sign. Any y in our equation is considered to be a function of x. And so whenever we come across a y and we have to differentiate it, we'll always be applying the chain rule when we're differentiating implicitly. All right, so let's just take a look at this. Again, this is review, but we haven't done it in a while, but hopefully once we go through the problem, it's going to ring some bells for you. So if we want to take the derivative with respect to x of the left side and the y side. We're going to have d dx of y squared plus 3xy is equal to d dx of 4x cubed. Okay, so now when we take the derivative with respect to x, again, anything that is a y is considered to be a function of x, so that's going to be chain rule. So the derivative of y squared would be 2y times the derivative of y, which would be dy dx, right? The derivative of our function y with respect to x. The next term right here, the 3xy, that is going to require chain rule, or excuse me, that is going to require a product rule because we have 3x being multiplied times y. So product rule, we're going to do first d second plus second d first. So my first d second is going to be 3x, that's my first. D second, well, the derivative of y is going to be dy dx, plus second, that's my y. D first, and the derivative of 3x is just 3. Okay, and then on the other side of the equal sign, the derivative of 4x cubed, that's just power rule. 3 times 4 is 12, so that's going to be 12x squared. Okay, now I'm going to just do a little bit of simplifying. Remember, what I'd like to do here is I'd like to find the derivative. Well, the derivative is dy dx. So ultimately, my goal here is to make this look like dy dx equals. So the first thing I'm going to do is these two terms right here both contain that dy dx, okay, right here and right here. So I'm going to factor that out. So I've got dy dx times, in the first term I have 2y, plus in the second term I have 3x. And then this right here, this 3y, I'm going to scooch over on the other side of the equal sign because that doesn't have a dy dx in that term. So on the other side of the equal sign, then I'm still going to have my 12x squared and then minus 3y. And then, of course, the last step to isolating dy dx would be to divide both sides by 2y plus 3x. So I end up with my answer being dy dx is equal to 12x squared minus 3y, that's my numerator, divided by 2y plus 3x. And there is the derivative of our function using implicit differentiation. In the next example, we are supposed to show that this equation, y equals 2/3 e to the x plus e to the negative 2x, is a solution of this differential equation, which is going to require us to do some substitution and some simplifying. And that's great, but if you look at our differential equation, you would note that it has both y in it and y prime. Well, we have an expression for y that was given. So our first job here is going to be to find an expression for y prime so that we have something to plug in for y prime. So I'm going to differentiate y, and this time I'm going to call it y prime because that's the notation that's used in my differential equation. So when I differentiate 2/3 e to the x, remember the derivative of e to the x is just e to the x, and any coefficient just comes along for the ride. So the derivative of the first term is exactly the same as the first term, 2/3 e to the x. The derivative of my second term is going to require chain rule because in my exponent I do have a -2 times x. So the derivative of e to the u is e to the u times the derivative of u, so times the derivative of -2x is going to be times that -2. So then this is going to be plus -2e to the -2x. And again, that's just chain rule. Okay, so now I am going to take that given function, which was y prime plus 2y equals 2e to the x. And my job is to show that this is true using my equation for y and my equation for y prime. So the next step is just going to be substitution. So for y prime, I'm going to plug in my 2/3 e to the x plus -2e to the -2x, plus, in my equation, my next term has to be multiplied by 2, so 2 times, and I'm going to substitute in what y was equal to, which was 2/3 e to the x plus e to the -2x. And this is supposed to equal 2e to the x. Again, just trying to make the left side look like the right side. So I'm going to distribute this 2. 2 times 2/3 e to the x is 4/3 e to the x plus 2 times e to the negative 2x. These two terms do not change. Okay. And now let's see what I have as far as like terms are concerned. All right, so it looks like I have a 2/3 e to the x plus a 4/3 e to the x. 2/3 plus 4/3 is 6/3, and 6/3 is 2. So I have 2 e to the x. And then right here, I have negative 2e to the negative 2x. And right here, I have positive 2e to the negative 2x, which cancel out. So I end up with 2e to the x equals 2e to the x. So check mark there, we did exactly what we were asked to do. We showed that this equation y is a solution to this differential equation, y prime plus 2y equals 2e to the x. In the next example, example number 5, we are looking for the values of r. For what values of r does the function y equals e to the rx power satisfy that differential equation? Very similar to what we just did in the previous problem, except if you look at our new differential equation, this equation contains both y prime and y prime prime. So we will need to find a first derivative and a second derivative of our function y. So we are given that y is equal to e to the rx power. Now, in this case, we are assuming, because they say for what values of r does this function satisfy the differential equation, we are assuming that r is some constant. So treat r as a number or as a coefficient. So then if we're going to take the first derivative, that would be y prime. That is going to be equal to e to the u, or e to the rx, but then times the derivative of the exponent. The derivative of r times x would just be r. So we end up with r e to the rx. And then our y prime, now again, keeping in mind r is a coefficient, not a variable. So this does not require product rule. This is just the derivative of r e to the rx, right? So r e to the rx, which is going to be itself, times the derivative of the exponent again, which is r. So then this gives me r squared e to the rx, because again, r is a number in this case. Okay, so now we're going to do the same thing as we did in our original problem, or our previous problem, sorry. We have 2y prime prime plus y prime minus, I'm going to parenthesize that, because remember, when you subtract, you have to subtract everything that you plug in, equals 0. We wouldn't want to make a sign error. That will mess things up. All right, so we're plugging in, my apologies, let's fix that. We're plugging in y prime prime, we're adding y prime, and then we're subtracting y. So we're going to have 2 times y prime prime, which is r squared e to the rx, plus y prime, which is r e to the rx, minus r, which is e to the rx. We don't have to distribute to anything. We only have one term, right? Equals 0. Okay, now if we're supposed to solve for r, let's take a look at what we have here. This looks to me like it's going to be some sort of a factoring situation. And I notice that I have a common term in all 3 terms on the left side of the equal sign, and that is e to the rx. So if I factor that e to the rx out, you'll see that I'm going to have something that looks much like a polynomial. So if I take out my e to the rx, then my first term becomes 2r squared, my second term becomes r, and my third term becomes minus 1. And that then factors, and again, you can factor this any method that you like. I just prefer to do guess and check. This is going to factor into 2r minus 1 times r plus 1 with my e to the rx equals 0. All right, so now we are back at the zero product property portion of the problem. We've done this many times before in Algebra 1. We have three things that are being multiplied together that equal 0. So let's find out what makes each of those factors 0. Well, e to the rx, there is nothing that would make this 0. This has no solution because there is no exponent on an e that turns an e into 0, right? E to the 0 power is 1, e to something positive is big, e to something negative is small, but there is nothing that's going to turn that into 0. However, here r would equal positive 1/2, and here r would equal negative 1. So this is the answer to our problem here. For what values of r does this function satisfy this differential equation? The answers are r equals 1/2 and r equals negative 1. However, there is a part B to this problem, which says that if r1 and r2 are the values of r that we found above, we need to show that every member of the family of functions y equals that is also a solution. So we're going to plug I'm just going to call this 1/2 here r1, okay? And I'm going to call this negative 1 r2. So that would mean that my y would be equal to ae to the 1/2 x plus be to the negative 1x, right? Plugging in my 1/2 for r1 and my negative 1 for 2. So now I'm supposed to show that this family of functions of the type y equals of this form also satisfies my differential equation. So once again, if I'm using that same differential equation and I have a y equals, I need to find my y prime and I need to find my y prime prime. So let's find the first derivative. So y prime is going to be equal to, okay, again, I've got something times e to the power, right? So I'm still going to have my ae to the 1/2 x, and then I have to multiply by the derivative of the exponent. The derivative of 1/2 x is 1/2. So the derivative of my first term becomes, let me write that a little clearer here, becomes 1/2 ae to the 1/2 x. And the derivative of my second term is very similar. I'm still going to have my be to the negative x, but I have to multiply chain rule by the derivative of the exponent. The derivative of negative x is negative 1. So this term becomes negative be to the negative x. And now I have to differentiate again. So y prime prime. Okay, same thing. I'm going to have all this 1/2 ae to the 1/2 x, but then I have to multiply by the derivative of my exponent, which is 1/2. So the 1/2 times the 1/2 is going to make 1/4 ae to the 1/2 x. And in my second term, the negative 1 from the exponent that I have to multiply is going to make the negative b become a positive b e to the negative x. All right, so now I have my y prime, and my y prime prime. So I can go back to that differential equation that I was given, and I can plug these in and show that the left side equals the right side, okay? So I'm going back to 2y prime prime plus y prime minus y equals 0, right? And a little question mark there because we're trying to show that this is true, okay? So when I plug in my y prime prime, I'm going to parenthesize it. So I'm going to have 2 times 1/4 ae to the 1/2 x plus be to the negative x plus my y prime, which is 1/2 ae to the 1/2 x plus negative be to the negative x. Now I have to be careful here, minus, and I am subtracting all of my y, ae to the 1/2 x plus be to the negative x equals 0. Sorry about the smush. All right, I'll spread out a little bit my next step here. So now I'm going to do some distributive property. 2 times 1/4 is 1/2. So my first term here is going to become 1/2 ae to the 1/2 x plus 2 be to the negative x plus 1/2 ae to the 1/2 x minus or plus negative be to the negative x. And then I have to distribute the negative, so I get minus AE to the 1/2 x and minus BE to the negative x equals 0. Okay, it is combine like terms time. Let's see what we have here. All right, if I just look at my AE to the 1/2 x terms, see here, I've got 1/2 AE to the 1/2 x, and I've got another 1/2 AE to the 1/2 x, and then I've got a negative AE to the 1/2 x. Well, 1/2 plus 1/2 is 1, and then positive 1 plus negative 1, well, those three terms end up canceling themselves out, right? And then my other like terms are my 2BE to the negative x and my negative 1BE to the negative x and my other negative 1BE to the negative x. But again, positive 2 minus 1 minus 1, it's going to make 0. So those three terms cancel out as well. And this is a true statement. All right, moving on to the next example. When we are applying differential equations, we're usually not as interested in finding a family of solutions as we are in finding a solution that satisfies some additional requirement or initial condition. And we are going to talk more about this in section 7.4. The type of problem that involves finding the solution of a differential equation that satisfies an initial condition is called an initial value problem. So we have this differential equation that we are given, x squared y prime plus xy equals 1. And we're supposed to show that every member of the family of functions y equals ln x plus c all divided by x is a solution of the differential equation. So again, since our differential equation contains y prime, we are going to need to find y prime. Ooh, it's been a while since we've done this. Y is a function that contains a quotient. So we are going to need to do quotient rule. We've got y equals ln x plus c divided by x. Okay, so what's my quotient rule? Low d high, right? And again, c is a constant, remember. So y prime, low is x, d high. Well, the derivative of a constant is 0. The derivative of ln x is 1 over x. So there's my low d high minus high, ln x plus c, d low, derivative of x is 1, and this is divided by low, which is x squared. Okay, so I can clean that up a little bit, make it look a little nicer. So my y prime is going to be equal to x times 1 over x. Well, that's just 1. I distribute 1 times ln x plus c is ln x plus c. I have to distribute that negative 1, so I get minus ln x minus c, there's my numerator, and my denominator is x squared. Okay, so next step is going to be to plug my y and my y prime into my differential equation and see what happens, right? So when I plug it in, my differential equation is x squared y prime plus xy equals 1. Okay, so let's plug in x squared times my y prime, which is 1 minus ln x minus c divided by x squared, plus x times y, which was ln x plus c over x, and that's supposed to equal 1. Okay, so now I do a little bit of simplification here. The x squared in the numerator and the denominator cancel in my first term, and again in my second term. So now I have 1 minus ln x minus c plus ln x plus c equals 1. Okay, and then when I start combining like terms to simplify, negative ln x and positive ln x, those are going to cancel. And negative c and positive c, those are going to cancel. So I'm left with 1 equals 1. True statement. The next part of this problem asks us to use a graphing calculator to graph several members of the family of functions on the same screen and then have a little discussion about what we notice. Just for the sake of time, I took the liberty of doing this ahead of time on my graphing calculator. Okay, so here's my y=, screen, and this is a whole family of these curves, these ln x plus some c value all divided by x. So I did c values of +3, +2, +1, 0, -1, -2, and -3. And I went ahead and I changed my viewing window because these are all log functions. We know that the domain they're going to be greater than 0. So I started with my x minimum at 0 and my x max at 10. And some of these they all go low. So I went just a y min of -10 and a y max of 6. Okay, so when we take a look at the graph here of all of these functions together, this is what this family of functions looks like. Okay, so you can see that they all kind of have that same general shape. And if we wanted to go ahead and make a graph of that general shape, we certainly could. And if you wanted to label each of these functions and color code it, you could, although I don't know that that's necessary. But we just want to kind of get an idea here of what these look like. Okay, so if I were to graph these, notice that kind of got something that looks like this going on, right? And then the next function doesn't go quite as high. And then the next function doesn't go quite as high. Whoops. Okay. And then the next function doesn't go quite as high. And then they start to do this, right? And I've got 7 functions graphed there. Okay, so that's the general idea of what we have going on here. Okay, so now let's make some statements about what we see. Okay, well, first of all, we can say they all have the same general shape. And the same domain, right? And the domain of all of these functions is going to be 0 to infinity. We could also note, because they kind of go in order of the biggest c down to the smallest c, so we could say the greater the c value, the greater the maximum value of the function is, right? Like up here, this is when c was 3, and over here, our max value is going to be like way over here on the graph, but our max value is obviously much lower when c is -3 than it is when c is +3. So we can say that the greater the c value, the greater the max value of the function. Okay, and then one other thing that I kind of wanted to point out here is that our c value has an effect on the x-intercept of the function. Okay, so when we think about what all of our functions look like, let me switch colors here. We've got y equals the natural log of x plus some c value being divided by x, right? Well, an x-intercept is when y is 0, right? So if we set this equal to 0, then we have ln x plus c over x. Okay, well, when is a fraction equal to 0? A fraction is equal to 0 when its numerator is equal to 0, right? So that means that whatever makes my numerator 0 is going to be my x-intercept of my function. Well, if I were to solve this, then I would get that natural log of x is equal to the opposite of c. And if I want to undo the log, then I have to raise both sides to the base of e, right, like this. So then I end up with the x value that would be my x-intercept for any of these values of functions is going to be e to the -c power, okay? So this right here is going to be the x-intercept of any of these functions in this family. And so the c value affects our x-intercept. Okay, so our parts C and D of the same problem we were working on, we're trying to find a solution of that differential equation that satisfies the initial condition y of 1 equals 2. Okay, well, what does that mean? First of all, that means that the point x is 1, y is 2 is on the curve. So hey, let's cheat for a second. Let's go back and let's take a look at our curves that we graphed here. Which one of them looks like it might have the point x is 1, y is 2? Everybody see right there that it looks like the red curve appears to have that initial value, y of 1 equals 2, which the equation for that function is natural log x plus 2 divided by x, which means our c value is positive 2. Okay, so let's do the math and let's see if that's the answer that we get. Okay, so what we're trying to do is take our function y equals ln x plus c divided by x, and we're saying when x equals 1, y equals 2, and we need to solve for c. That is our job right now. Okay, so let's do it. Y is 2, so I'm going to plug in 2 for y, equals x is 1 over 1. Okay, well, ln 1 plus c divided by 1 is just ln 1 plus c, right? So we end up with 2 equals, and the natural log of 1, well, that's 0. So we end up with 2 equals 0 plus c, which tells us that c equals 2, okay, which was what we suspected when we looked at that graph, right? Okay, so this means that our equation is going to be y equals natural log x plus 2 over x. Okay, that is the differential equation, or the solution that satisfies that initial condition of our differential equation family. All right, part D, we're doing the same thing, but this time the initial condition is y of 2 equals 1, or when x is 2, y is 1. Okay, let's take a peek at our graph again and just see what we can see here. All right, when x is 2, y is 1. Okay, well, it looks like it could be the black curve, but I'm not feeling 100% on that. We could do a little trace here, right? Or a second level calculate a value. And if we want to calculate it on the black curve, hang on, which curve are we on here? Where's our cursor? Gotta bring that back in. I'm not sure where my cursor is here, but let's do x equals 2. Oh, here we go. If I want to jump, I want the black curve, right? If x equals 2, ooh, y is not quite 1, okay? So when x equals 2, notice that on my red curve, y is 1.34, and when x equals 2 on my black curve, y is 0.846. So what that tells me is none of my curves up here represent this particular solution that we're looking for in this problem. Doesn't mean we can't find it. It just means that c is probably not going to be a whole number, okay, or an integer. That's fine. Let's figure it out. We're going to do the exact same math. So we've got our equation, ln x plus c divided by x, and this time when x is 2, y is 1, and we want to solve for c. So let's see, we get 1 equals natural log of 2 plus c divided by 2. All right, well, if I want to get that 2 out of the denominator, I'm going to multiply both sides of the equation by 2. So 1 times 2 is 2 on the left-hand side equals natural log 2 plus c. And if I want to get c alone, then c is going to be equal to 2 minus the natural log of 2. Natural log of 2 is not a nice number. It's a decimal. So we're just going to leave our c value in terms of natural log 2. And then we're going to plug that into our function, which is y equals natural log of x plus c, so plus 2 minus ln 2 divided by x. And that is our answer to this problem.